Assalamu alaikum. I welcome you all to the second episode on rectifiers. In the last class, we discussed about the half wave rectifiers with various kind of loads, including the pure resistive load. Then we studied the RL series load. Thereafter, we studied the RL series load with a DC source connected on the output. We also studied the use of freewheeling diode to get rid of the negative portion that appears on the output of a rectifier in case we have the inductance presence on the load side. In today's class, we will see the effects of source inductance on the device commutation, and we will analyze the impact of the current commutation on the output voltage available for a rectifier. So let us start with today's class. Now in this topic, we will discuss the impact of having a finite AC side inductance on the circuit operation. The inclusion of LS in the circuit of a half wave rectifier that I am drawing right now. This is sine wave source. Here we have the diode, and here we have an RL load. Let us also connect a freewheeling diode here. So for the analysis of the source inductance, we will follow two critical assumptions. Number one, that the diode D1 as well as this diode D2, they are considered ideal, so that whenever we have the potential difference between the anode to cathode is equal to 0 volt, they conduct. The second assumption is that this load, which is a combination of L and R, the dominant part lies with the inductance, and therefore the load is highly inductive, and this implies that due to this high inductance present on the load side, we have a constant current flowing through the output load, and therefore we can represent this as a current source. So together, when we combine these few assumptions, then the circuit looks like this one. So now we have, this is I0, this is V0. The current flowing through this diode D2 is termed as ID2. This is D1. This is LS, which is the line inductance, and this is the voltage across this line inductance. This is VS T, which is equal to Vm sine omega t. Now this portion which constitutes the source and this inductance is a better approximation or a better representation of a utility, because we have the inductance present in the transmission lines and the distribution network of the electrical power system. Now we need to see impact of LS is directly on the transition of the AC current, which will not be instantaneous like the case we have discussed in the last lecture. So first of all, Let us draw the waveform for this particular circuit where we do not have any source inductance present. So for this, this is the sinusoidal waveform, which is Vs, and for a very highly inductive load, this waveform represents the source current Is, and this source current is having a stiff value because we have represented a constant current source connected across the load. Further to this, we have V naught. That V naught is a sine wave for this positive half cycle, and it is 0 for the negative half cycle. We have this equal to V naught. This is Vs and V naught, and this one is this Vs. So this looks like exactly the circuit with only the resistive load. However, the inclusion of a constant current source on the output showcase that we have this Is of this particular shape. It is having a constant value. Because of the presence of this D2, we do not have any negative portion, and consequently we are getting the same sort of an output, just like the half-wave rectifier with only the resistance across the output. Now let us concentrate on this particular circuit where we have the inductance available. Now, prior to this time, if this is omega t, here we have 0. For omega t less than 0, we have a negative half cycle here. And therefore, this voltage Vs is negative, and consequently the diode D1 is turned off. D1 is off, and in order to have the current flowing across the output load, we have this D2 conducting, and therefore this I naught, it circulates through the diode D2. Consequently, we have a short circuit path here, as we have discussed in the last class. So we have V naught t equal to 0, and on the same time we have the source current Ist. This is also equal to 0. Now at this particular time instant, omega t equals to 0, at this particular instant here, the D1 conducts. So at omega t equal to 0, when D1 conducts and hence it is in a forward bias state, the overall circuit looks like this one. We still have this diode on, which is the freewheeling diode, and here we have the load current I naught. This is Ls, this is D1, this is D2. So this Is is equal to the ID1, and here we have the ID2 here, which is the current which was circulating prior to the omega t equal to 0. This is Vs t, which is the source voltage. Now with the presence of this source inductance Ls, the current will not rise instantaneously through this diode D1. Rather, the current Is starts to build up, and in that particular process we have this D2, it is also conducting. So we have for this much period of time, when this D2 is conducting, we have this D1 conducting, this V naught is equal to 0 because it's a short circuit. D2 is forward biased, so it is creating a short across the load. So if we analyze this particular circuit, there are two mesh currents which are flowing in the circuit. The first mesh current is this one, which is the IS, and the other mesh current is this current, which is this I naught. And if we apply the basic theory that we have studied in the basic linear circuit course, then the current which is flowing through the path of this D2, ID2, is equal to the difference between the current I naught and this current IS. So that is equal to I naught minus IS. As we have the sinusoidal waveform, we have, this is the shape of this VST. This is the sinusoidal applied voltage. So we have a gradual build up of the source current IS to a value where this IS becomes equal to this current I naught. And this rise of current IS from 0 to the value I naught, this process requires a finite time because of the presence of this source inductance LS in this given circuit. As soon as we have this IS equals to this I naught, this D2 becomes reverse biased when this IS becomes equal to this I naught. And this whole process is going on and it's taking a finite time, which is known as the commutation angle or the commutation interval. We call it U. So from this 0 across this omega t, a finite time is required during which the output voltage is 0 and the current IS builds up to a value which is equal to this I naught. So as IS becomes equal to this I naught, then according to the mesh current analysis that we have performed here, this ID2 becomes equal to 0 and thereby D2 turns off. Now we should note one thing here, that the source current IS which is flowing from this utility, it cannot exceed the value of this ID, because doing so shall have a negative current flowing through this D2, and because this D2 is a single quadrant device and it only operates in a positive current quadrant with a positive current value, it do not allow a negative current. So when D2 stops conducting, then this IS value becomes equal to the value which is the output current I naught. So here we understood two things. The first thing is that we have the finite time interval requirement for the transition of load current from one device, which is in this case is D2, and it shifts the burden to this T1, is called as current commutation. Current commutation time or commutation interval. And it is represented as as u, small u. So this is the commutation interval. So what is the commutation process? In fact, the process of commutation is the process where the current conduction shifts from one diode or from a set of a diode in case of a full wave rectifier to another is called current commutation process. And this process of commutation leaves its impact on the output voltage available. So let us draw the waveforms for this particular circuit and analyze a few important things here. So let me first of all draw the waveforms. This is Vs, which is the source voltage. This axis is omega t. This is omega t. Now, for the commutation interval u, since the diode D2 is conducting, therefore the output voltage V0 shall be 0 for this entire duration. So let us say that we have this type of output voltage. This is V0 t, and this V0 t becomes equal to 0 for the negative half cycle, because we are only considering it for a half wave rectifier. The other important point here is that for any given circuit, we have the establishment of KVL provides us an important value. So if we apply the KVL here in this mesh number 1, then the portion when this VST is not connected with this output voltage V0, that portion is dropped across this, or it appears across this inductance LS. Therefore, if I plot this VLS for this particular duration, then this is the voltage which appears across the inductance VL. Similarly, we have a negative portion for this VL as well during the time when we shift the load from the diode D1 to the diode D2. So the area which is here, which is confined here, this area, this might be of our interest. The area AU, or the area which is confined during the commutation time U. So this is U, which is the commutation interval. As far as the source current is concerned, the source current shall have a slow gradual rise, here, and it moves all the way to this particular point, and here it becomes equal to 0. So this is IS, and this duration, as I have said, U is of our interest because it provides us some important information. Now we need to establish that what determines the duration or the length of the commutation interval U. This is of our interest, and we want to establish the duration of the length of the interval U, and for this we will consider the voltage across the inductance or voltage across the line inductance LS. So during this particular U, the KVL yields that we have VLS is equal to VST, because this is the equivalent circuit. This is the equivalent circuit. So if I apply the KVL here, this is VST, so plus minus VLS, because this is LS, which is the source inductance, and therefore this is equal to VST. This means that we have Vm, which is the peak value, sine omega t, that is equal to Ls dis over dt, and this is for omega t to u. So it is only between this green portion that we have the voltage across the inductance, because right after that we have a constant current, which means that the rate of change of the current is 0. So consequently the inductor behaves like a short circuit. So this becomes equal to Vm sine omega t d omega t, and that is equal to omega Ls d is, and let us say this is our equation number 1. Now if we integrate this equation such that we know that the source current moves from this 0 value to this point, which is equal to this ID, or this, the I naught, and this whole happens between the time from 0 to u, then if I integrate this thing, we get 0 to u Vm sine omega t d omega t, and that is equal to omega Ls 0 to I naught d is, and this whole is equal to omega Ls into this I naught. And let us say this is equation number 2. In here, if you see, this particular portion is the volt, not the second, because it is in omega t, so it is the volt radian area AU. So I can find out the area which is confined under this duration 0 to u, and I can calculate this as AU is equal to 0 to u Vm sine omega t d omega t, and this is equal to Vm into 1 minus cosine u, and let us say this is my equation number 3. Now from these equation 2 and 3, I can say that this AU, which is equal to Vm 1 minus cosine of u, is equal to omega Ls I naught, and if this becomes my equation number 4, then this equation tells us some important information about the commutation. It tells us that the commutation voltage over the entire duration of the commutation is actually a product of the frequency, the source inductance, and the output current I naught. So from this I can find out what is this cos u. This becomes equal to 1 minus omega Ls I naught over V maximum, which is the peak value. This becomes my equation number 5, and this equation further tells me some important things. It tells me that if we have Ls equals to 0, then this cosine of u becomes equal to 1, and this represents that we have u equals to 0 degree, and consequently we have the starting of the current Is right at this time instant omega t equal to 0. So one thing is understood, that this equation tells us very good expression or very good information about the effect of the source inductance on the output. Further to this equation 5, it provides us some interesting information. It tells us that the commutation interval u, or the duration for the commutation to happen, it increases with the increase in the source inductance. It also increases with the output current. Higher the output current, higher is the commutation interval time, and it decreases with the increase in the applied peak voltage Vs. So right now that we have seen that by adding the source inductance into the circuit, there are some string things which are happening for the source current, but the overall the impact of the commutation interval on the overall circuit is the reduction in the output voltage, is the reduction in the average output voltage. So for example, we consider this particular circuit. We have this sine wave. Here we have this diode D1. This is D2, which is a freewheeling diode. And here we have the output current I0. For this particular circuit, the V0 here, the average value of this V0 is equal to 1 over 2 pi 0 to pi Vm sine omega t d omega t, and this results in a value which is equal to Vm over pi, where this Vm is the peak value of the applied AC waveform. Now if we have an inductance here, if we have the inductance here, right, this is Ls, then what happens that we can visually see the impact of the commutation. So with this thing, now we have this V0 that is equal to 1 over 2 pi integral 0 to pi V of m sine omega t d omega t, and this, instead of starting from 0, because of this inductance, it will start from the time instant omega t equal to u, and it ends at omega t equal to pi. And therefore the expression here gives me 1 over 2 pi. One is from 0 to pi, which is a standard expression for the circuit without the source inductance, and then we have 1 over 2 pi 0 to u Vm sine omega t d omega t, where this portion in the average output voltage, it represents the reduction in the average output voltage. So the average output voltage V0, it is equal to Vm over pi minus the area AU divided by 2 pi, and this gives me an expression that is equal to Vm over pi minus omega Ls I0 divided by 2 pi. So in a nutshell, we have seen that the inclusion of the source inductance not only represent a better modeling of a utility, it also provides us an important aspect that the overall output voltage, the average output voltage which is available, the overall output voltage actually reduces. So in the next class, we will discuss about the half rectifier with the C filter. So till then, take care and Allah Hafiz.